Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. A hurricane is perhaps nature's most terrifying expression of fluid dynamics. It is a monumental engine of chaos, a sprawling, violent vortex where winds hit hundreds of miles per hour. But beneath the surface chaos, mathematicians and physicists believe there is a hidden, beautiful order. An order defined not by conventional physics, but by high-dimensional topology, specifically, the Hopf Fibration. We usually describe atmospheric flow using classical mechanics, focusing on velocity, pressure, and temperature fields in three-dimensional space. But the moment a fluid becomes turbulent, like in a hurricane, this description breaks down. The vortex lines, which track the rotation of the fluid, begin to twist, stretch, and intertwine in ways that defy simple algebraic analysis. These lines become so complex, so hopelessly knotted, that predicting their long-term behavior is almost impossible. This is the fundamental challenge of turbulence, often called the last great unsolved problem in classical physics. To solve this, scientists are turning to geometry that exists outside our immediate perception. They are using topology, the study of shapes and spaces that remain unchanged under continuous deformation, and placing the chaotic 3D vortex field of the hurricane onto a higher dimensional structure. The three-sphere, or S3. Imagine the surface of a standard balloon. That's a two-sphere, S2. The three-sphere is the set of all points equidistant from a center point in four-dimensional space. While we can't visualize 4D, we can describe its mathematical relationships. This is where the Hopf Fibration comes in. Developed by Heinz Hopf in 1931, it's a mapping process that takes the three-sphere, S3, and separates it into an infinite family of perfect, non-intersecting, nested circles. These circles are called fibers. Critically, these circles are topologically linked together. If you take any two fibers, they are always linked exactly once. Picture two perfect, interlocking smoke rings that never touch but are fundamentally intertwined. So, how does this structure relate to atmospheric turbulence? Physicists map the velocity field of the hurricane onto the three-sphere. When the flow is defined by the Hopf structure, the chaotic, intertwined vortex lines of the hurricane, which are 3D curves, are transformed into the perfectly structured, non-interlocking fibers of the S3 space. In this topological framework, the vortex lines of the storm are no longer arbitrary, messy curves. They become defined paths. The mathematics reveals a crucial quantity, the Hopf invariant, or Hopf index. This invariant counts the number of times the vortex lines are linked together. In a classical fluid, the Hopf invariant corresponds exactly to the helicity of the flow, a measure of how knotted and coiled the fluid streamlines are. This helicity is a conserved quantity in ideal fluids, meaning it doesn't change over time. By mapping the atmospheric turbulence onto this stable topological framework, scientists can identify structures that are inherently stable, carrying significant energy. A high Hopf invariant suggests a highly organized, stable vortex structure, like the tightly wound eye wall of a Category 5 hurricane. Low numbers suggest rapid dissipation and instability. This shift in perspective is profound. Instead of trying to calculate the trajectory of every single air molecule, a computationally impossible task, physicists use topology to describe the underlying structure of the flow. They are not looking at where the air is, but how the space itself is topologically organized by the flow. This high-dimensional approach offers predictive power far beyond traditional models. By tracking the evolution of the Hopf invariant, researchers can potentially determine when a storm structure will stabilize and intensify, or when it will collapse into chaotic dissipation. Furthermore, this method is universal. The Hopf Fibration is used to model everything from the quantum spin of particles to the stability of magnetic fields in plasma. Its application to meteorology suggests that the very same deep mathematical principles govern the subatomic world and the colossal storms that ravage our planet. Ultimately, the Hopf Fibration provides a lens through which the overwhelming chaos of atmospheric turbulence reveals its elegant, high-dimensional architecture, bringing us one step closer to truly mastering the prediction of nature's most violent phenomena. For more incredible facts like this, don't forget to subscribe and turn on notifications.